Hello everyone, welcome to module 3 of design of steel structures. Today we will be talking about the wind actions in Australia. So welcome to week 3. This module is introducing the calculation of wind speeds and resulting action using the relevant Australian standard. As you know, it is 1170.2. The latest version of this standard is 2021 version, so please have a look on this one. The topics of this week are calculation of wind actions, regional wind speeds, site exposure multipliers, aerodynamic shape factor C shape, dynamic response factor C dynamic. So this week we are focusedly talking about wind load calculation. Okay, the sources and readings for this week are the Australian standard itself, 1170.2 2021, structure design action part 2, wind actions. The second source or the second readings you can have a look on is the textbook steel structure design manual to AS 4100 from page 26 to 40. This is talking about wind. But unfortunately, this is talking about outdated version of Australian standard 1170.2, which is 2002. So some of the equations have been changed. So the first point we have today, or the first section, is calculation of wind action. And here's some introduction about wind action. The pressure exerted by the wind on any part of the structure depends on shape of the structure and wind direction. In windward walls and upwind slopes of a steeply pitched roof, there is a rise in pressure above the atmospheric pressure. So the pressure will be above the atmospheric pressure. For side walls and leeward slopes of roofs and flat roofs, there is suction on outside. So the external pressure is suction. Greatest suction pressures near edges of the roofs and walls. So the maximum suction is near to the edge. Okay, for the internal pressure can be positive or negative. Positive means compression, and negative means suction. So positive pushing walls or roof outwards. So in this case, dominant opening on the windward side only. So the opening will be on the windward side only to have this case. For suction, sucking inwards, the walls or the roof, the opening in this case are on the side wall or leeward walls. This is explained in these two figures or these two shapes here. As you can see, if this is the wind direction and we have opening here, so this opening in the windward direction, you can see that all the internal pressures are, as you can see, pushing the wall and the roof, so it is positive or compression. The other case, if you see the wind direction here, and you can see that the opening here in the leeward wall, so you can see that there is suction on wall and suction also on roof. So this is like some explanation of the direction of the internal pressures. The next point is extreme storm wind gusts usually cause damage. It varies in time, space, considered by Australian standard. It is uneconomic to design structure to remain totally undamaged even in extreme storm, which occurs one in hundreds of years. So this is not a good procedure to design to withstand the rare events like storm, extreme storm. It is normal to use two wind speed in design. We have two wind speed, ultimate wind speed, used for ultimate limit state, as you know. And the next one is surfaceability wind speed, which used for surfaceability limit state. The ultimate the ultimate wind speed is unlikely to occur during the structure's life, but could occur at any time. Some minor damage is acceptable, but the structure must not totally collapse. So for the ultimate, minor damage, but not total collapse. For surfaceability wind speed, a lower wind speed is used, which is like ultimate wind speed over almost 1.5. So this gives us WS or W surfaceability. So it is lower in value or lower wind speed is used. Structure so survive without damage. So the difference between surfaceability and ultimate is it should be no damage happen. We have to note that all calculation equations related to the wind speeds are related to 1170.2 2021, which is the latest version of the standard. So the first point in our calculation is site wind speed. Site wind speed, V set beta, which you can find it in clause 2.2. The site wind speed for the 8 cardinal direction and beta at reference height Z above the ground surface. So we have to calculate V side beta for 8 cardinal direction, beta at reference height Z above the ground. So the equation or the formula for V side beta is from the Australian standard, as you can see, VR MC MD MZ cat MS MT. So we have VR, which is regional wind speed or a type of wind speed or regional wind speed. And all these are parameters. So we have 5 parameters and 1 speed to find beta side beta. V side beta. So the definition of the parameters we are calculating in this equation are VR is the regional gusset wind speed in meter per second, so in meter per second, for average recurrence interval R in years as given in section 3 of the Australian standard. So we will go to this one now. If we go to section 3, as you can see, this is just to show you what is meant by that. This is the regional wind speed. This is the region, the wind region in Australia that the wind speed are given, and you can find the regional wind speed in this table, table 3.1a, as you can see, according to the region, non-cyclonic and cyclonic, A, B1, B2, C, and D. So this all is to calculate regional wind speed. So firstly, we know that we will get VR from section 3. MC is the climate change multiplier. MD is the wind direction multiplier for 8 cardinal direction beta. MZ cat is terrain height multiplier. MS is shielding multiplier. MT is topographic multiplier. So as we said, we have 5 parameters to calculate, and the regional wind speed. So we have all these parameters to find the site wind speed. Generally, the wind speed is determined as the average height, roof height, h. In some cases, this varies according to the structure, as shown in this figure. So here, because as you can see, there is this height, this height, this height. So h is the average height. Here as well, this is another case to find the height. Here as well, this is the height is, so the average is this at this point, so this is height. Here the height is like regular height, all points are same, so this is h. So this is the reference height of structure according to the Australian standard. In this video, this is optional video to watch, showing you the wind direction and wind speeds. The next point is design wind speed, V design theta. This can be found in clause 2.3 in the Australian standard. The building orthogonal design wind speed V theta shall be taken as the maximum cardinal direction side wind speed. So from side wind speed, you have 8 speeds. So the V design will be one of them, linearly interpolated between cardinal points within a sector of plus or minus 45 degree to the orthogonal direction being considered. Okay, so if we look at this figure here, so this is the figure showing the 8 orthogonal direction, like this one, as you can see here. So this is the 8 cardinal direction. So if you are designing a building in real life, so you have to consider the 8 wind speeds and then select the design wind speed based on the maximum direction. And you can see here, there's this like 90 degree, beta is 90 degree, here theta is 0. So this is the range we are talking about. And these are the bending orthogonal axes. This is like, you can consider it as y dash. This is x dash. So you can take the axes are orthogonally. This is the interval to calculate the wind in 45 degree, 45 degree. So this two direction will be your wind actions, or the wind actions if they are the critical. So you will take this two if they are the critical site wind speed. So the V design theta is depending on V site. So V design or design wind speed is depending on site wind speed, which is the maximum of the 8 wind speed. We have to note that V design equal to the maximum value of site wind speed in the range of beta from theta plus or minus 45. So if this theta, if you are considering this direction, so the design wind speed will be the maximum of these two in the range of 45 plus or minus 45 degree of the direction you are calculating for. And you have to do this for each direction, where beta is the cardinal direction clockwise from true north, and theta is the angle to the building orthogonal axis. Okay, for ultimate design state for ultimate limit state design, V design shall not be less than 30 meter per second. So V design theta is greater than or equal to 30 meter per second. The next point we have is the design wind pressures and distributed force. You can find this in clause 2.4 in the Australian standard. So the design wind pressure B is in Pascal, is BA, are calculated for structure using the following equation. So this is the equation to calculate the pressure or the design wind pressure, and the value will be in Pascal. The parameter in this equation are B, which is the design wind pressure in Pascal, can be BE, B external, B internal, or B in, B net. So B external, B internal, or B net. Depend on the case you calculate, where the sign is given by CB, values used to evaluate C shape. So this all for B. The next parameter is rho air. Rho air is the density of air, which can be taken as 1.2 kilogram per meter square. So kilogram per cubic meter, sorry. So the density is 1.2 kilogram per cubic meter. The next parameter we have is V design theta. So this is half, this rho air. This V design theta we get as design wind speed before. Which is the building orthogonal design wind speed, usually 0 degree and 90 degree, 80 degree, and 70 degree. So you can, or you have to calculate the design wind speed for 4 direction, 0, 90, 180, and 270. And this all depend on V site beta. That's why the design of wind or the calculation of wind takes a lot of time and effort if you will calculate all the direction and all the wind speed in real life. But for exam or assignment, we will not require to calculate all these direction. So we have to note that for some applications, V design may be single value or may be expressed as function of height. For example, windward walls for tall building more than 25 meter. The next parameter we have is C shape, which is a aerodynamic shape factor given in section 5. C dynamic is a dynamic response factor given in section 6. The value is 1 except for structure is dynamically wind sensitive. So the other parameter we have is C shape and C dynamic. As you can see here, this is 2 diameter. This is given in section 5. This is given in section 6 in the Australian standard. So if you find all this parameter, you can find the pressure, the wind pressure, and then after the wind pressure, you can calculate the wind force and then use it in design. So this equation is the most important equation we have because it gives us the pressure which we use to design. The next topic or the next section we have, or the next point we have, is wind actions, which is in clause 2.5. In general, wind actions W ultimate and WS for use in the Australian standard shall be determined as given in clause 2.5 and 2.4, and deflections and excavation of dynamically wind system structure as given in 2.5.7. So wind actions are W ultimate WS are this in 1170.0, which are the wind load ultimate, that's what has U, and WS is wind load surfaceability, which is used for the surfaceability limit state design. So the direction of the wind actions shall be derived by considering wind from no fewer than 4 orthogonal directions aligned to the structure. So the standard require to calculate the wind in 4 directions at least, which mentioned before, theta equal to 0, 90, 180, 270. So the forces, how to calculate the forces? The forces on surface or structural elements. We have two methods to find the forces, or two procedures. Force derived from the wind pressures. So after we get the wind pressure as previously, B, you can find the force F from this. So the wind forces F in newtons on surface or structural element is determined as a vector sum of the forces calculating using the applied pressure on the areas A as follows. So F is the force, will be equal to B is the wind pressure, where A is the area. So this is like a vector because you can have more than one pressure on a surface. So it is like a summation. So where is Bz is the design wind pressure in Pascal normal to the surface at height Z. Note, we have to note that the sign convention, because we have signs here. So like this is if the force going down like inwards the surface, so this is positive, or pressure, or we can, let's say, compression. And in some cases we have this internal, so this is also positive because it is compression. In some cases you have the pressure is going outwards, which is negative because it is suction. So the sign convention for pressure leads to the force towards the surface for positive pressure, forces away from the surface for negative pressure. So positive pressure is forces towards the surface. Negative pressure forces away from the surface. So this is important notice here. The second parameter we have is AZ, reference area in square meter at height Z, upon which the pressure at height BZ acts. So this is the reference area in square meter. So AZ in square meter, BZ in Pascal, and F in Newton. For enclosed building, which is our focus, so we are focusing on enclosed buildings. Internal pressure shall be taken act simultaneously with external pressures, including the effect of local pressure factors KL. So this means that if this inside the building, or this our building. So this is internal pressure, and this is external pressure. So you can consider both internal and external are acting simultaneously, and by considering the local pressure factor Kl. Generally, most of severe combination of internal and external pressure shall be selected for design, but some reduction in the combined load may be applicable according to this clause. The next one we have, or the next point we have, is the forces derived from force coefficients. In some cases, we have to get the forces using the force coefficients, not by pressure. So there is two procedures. This is the second procedure. So in Appendix C and D in the 1170.2 cover a structure for which shape factors are given in form of force coefficient, not a pressure coefficient. In these cases, determine the wind action. You cannot find it from the pressure, and you can find it only from the forces. So this is our equation. As you can see, it has a similar formula, but instead of B, we have now F, which is the force. Here, rho air is the same, 1.2 kilogram per cubic meter. V design is the design wind speed. C shape is the aerodynamic shape factor. C dynamic is the, as we mentioned here, C dynamic was the dynamic response factor. And AZ is the area. So AZ is as defined in clause C4 for lattice tower, or A is L times B for members and simple sections. So this is the main focus of our, if we need this formula, so we'll use this one. So which is means the area equal to L times B, or width times length, or can be defined as A reference as defined in Appendix D for flags and circular shape. So for our simple members and sections, we are using L times B, which is width times length, for example. The second topic for our lecture today is the regional wind speed. So regional wind speed is as we mentioned earlier, VR is required to calculate the site wind speed, which is V site beta. So the regional wind speed VR is depending on that Australia is divided to 5 regions for wind: A, B1, B2, C, and D, where A is divided to A0, A1, A2, A3, A4, A5, and then beta B1 and B2, then C, then D. So we have 1, 2, 3, 4, 5 regions. These regions are here in colors, and from this source. So this is if the, like, for example, if we are like in this area, the light yellow one here, region, this is region A0, which is a little bit far from the coast. Here, this area you can see A1. Okay, here the green is light green is B2, the purple is region D, or the dark pink. The sky blue is region C. Here, the dark or the green is B1, and here is the gold is A2. So, and here the orange is region 4, A4, and here the dark orange is A5, and here also the orange is A3. So this all the location or the region of Australia. So as you can see, or in later we will know that region A and B1 and B2 are non-cyclonic regions. C and D are cyclonic regions. So you know that these two regions will have larger values of wind or extreme wind speeds compares to A, B1 and B2 because these are non-cyclonic. Okay, so this is a figure from another source just to show the color so it may be more clear to you. And next is table, and also this is a map from the Australian standard itself. As you can see here, it has more details of the cities. That might be better for you to use when you're searching for your city. And here is wind regions from 11 this AS 1170.2. So as you can see, here it is in black and white. For example, if we're looking at Adelaide city here, so Adelaide in region A5. If we are looking at, for example, Canberra here, it is in region A3. And here, for example, Port Hedland, somewhere here, it is in region D. So you can find your city or find the city or the building are constructed at using this map or the colored map here. Both are same. And now we jump to the table A1, which gives the regional wind speed in Australia. The regional wind speed in meter second depend on the region. So A from A0 to A5, this column, from B1 to B2, this column, C and D, these two columns. But here, what is V1, V2, V5? This is called the probability of occurrence here in note 3. So for ultimate and serviceability limit speed, refer to National Construction Code, which is called NCC 2022, Volume 1, which give us for information on values of important level and annual probability of exceedance appropriate to for design of structure. So these numbers are called annual probability of exceedance depends on importance level of the building. Okay. For importance level 2, it is 1 to 500. So for example, importance level equal to 2. So the occurrence level or probability of occurrence of exceedness is 1 to 500. So we will design on V500. So if we are in zone A to 5, it will be 45, B1 or 2, 57, and C is 66, and D is 80. So you can find this information of the importance depending on the importance level from NCC volume 1. So depending on the region and the probability of exceedance, you can find the regional wind speed VR, where here R is defined as average recurrence interval, which is the average time interval between the exceedance of the listed wind speed for ultimate or serviceability wind speed. For ultimate, for R more than 5 years, it is equal to the reciprocal of the annual probability of exceedance of wind speed. Okay, if you have a look also at the last row in the table, so this is the formula where they get these values of wind speed. So it is 67 minus 41 r to the power negative 0.1 and so on. So if you know what is r or what is the r you designed for, so you can substitute here and get the original wind speed. The original wind speed for all directions, VR for all direction based on the peak gusset wind. So VR is based on the peak gusset wind for the wind regions in figure 3.1a from are presented in the table. Okay, so this is for this table here. So I think there is a mistake here. Just this title or this paragraph should be before the table. So the next parameter we are looking at after the wind speed is the wind direction multiplier MD. Okay, where is MD? MD was in, if we go up, to the site wind speed formula. So this is MD. So now we know MR, so the next is MD. So from the equation of V site beta or site wind speed, we need to know the site. To know the site wind speed, we need to know the wind direction multiplier MD. So the wind direction multiplier MD is taken as 1. So it will be taken as 1 in some cases as follows. If the structures are chimneys, tanks, and walls with circular or polygon cross sections and cladding and immediate supporting structures on building, so these two cases you can take MD as 1. For other cases, like normal building, the wind direction multiplier is the MD for all regions are taken as below table. So table 3.2a is the wind multiplier in Australia. Did always mention that it is in Australia because this is standard also for New Zealand. So there is some parts is for New Zealand. Okay, so now this table gives us the wind multiplier, the wind direction multiplier MD. So depend on the region, like let's say we are in region A2, and depend on the direction you are calculating for, cardinal direction. Let's say you are south direction. So this will be our MD. So MD in this case is 0.95. So this is MD, just simple multiplier. The next multiplier is climate change multiplier MC. So MC also is used to calculate V site or site with speed. So the climate change multiplier MC is taken as the following table, based again on the region. So MC depends on wind region. So if you know the region, let's say again A2 or sorry B2 or C and whatever the M region is. So this is 1.05. This is the wind or climate change multiplier. The third topic in our lecture today is the site exposures multipliers. So in general, the site exposure multiplier are parameters related to the site condition. So these parameters or multipliers depend on the site condition, which is the terrain or height multiplier, MZ or category, shielding multiplier or MS, topography multiplier or MT. So we have MZ and MS and MT, three site exposure multiplier. Okay, so the firstly for the terrain multiplier MZ, what is the terrain category definitions? Or so we are representing the terrain category with the symbol TC. Terrain over which the approach wind flows towards a structure is assessed based on the following categories. So we have like 5 categories to assess the terrain category. Number 1 is terrain category 1. So we have terrain category 1 or TC1. We have TC2. We have TC 2.5. We have TC3 and we have TC4. So to know or to calculate or to determine MZ, first of all, we need to know TC or the terrain category. For terrain category 1, it is very exposed open terrain with very few or no obstructions and all water surface. Example, flat, treeless, poorly grazed plains, open oceans, rivers, canals, and bays and lakes. So it is like open areas without no obstruction. 2 is terrain category 2, which is open area including grassland with well scattered obstructions having heights generally from 1.5 to 5 meter with no more than 2 obstruction per hectare. For example, farmland, cleared subdivisions with isolated trees or uncut grass. 3 is terrain 2.5 or TC 2.5, which is terrain with some trees or isolated obstruction. Terrain in developing outer urban areas with scattered houses or large acreage development with more than 2 or less than 10 buildings per hectare. D is terrain category 3 or TC3, which is terrain with numerous closely spaced obstructions having height generally from 3 to 10 meter. The minimum density of obstruction shall be at least 10 house size obstruction per hectare, like suburban housing, light industrial estates, or dense forests. E, which is terrain category 4. So terrain with numerous large, high, 10 to 30 meter tall and closely spaced construction, such as large city centers, well-developed industrial complexes. Okay, so here is the severity of terrain category. So when you go from TC4 to TC1, the severity of the terrain category increased. So selection of terrain category is made considering permanence of the obstruction that constitutes the surface roughness. So the obstruction should also be permanent, not temporary obstructions. Otherwise, it will affect the design later. The next point is determination of terrain height multiplier, which is MZK. The variation with height Z of the effect of terrain roughness on wind speed, terrain and structure height multiplier is taken as the following table. So if we look at this table, so table 4.1 is the terrain height multiplier for gusset wind speed in fully developed terrain for all regions except for A0. So for all other regions, like from A1 to A5, B1, B2, C, and D, for all these regions, to find the terrain multiplier, MZCat, you need to know the terrain first. So this parameter again depend on TC. So let's say if we have TC equal to 2.5 and we have like the height of the building is 30 meter, so MZCat will be 1.06. For region A0, as a note here, use MZCat2 for all Z less than 100 meter in all terrains. For 100 meter, take MZ as 1.24. So we have MZ cat 1.24 and what will be MZ cat 2 from the Australian standard. So if less than 100 meter, MZ cat 2. For 100 to 200, 1.24. For all other regions, for intermediate terrains, use linear interpolation. For intermediate values of Z, use interpolation. So for all parameters in this standard, you can use linear interpolation if you have a value intermediate between two values. The second multiplier we have is the shielding multiplier, MS. Generally, shielding is provided by upwind buildings or other structures. Shielding cannot be provided by trees or vegetation. So trees are not shielding. It cause or it affects the terrain category, but doesn't affect the shielding multiplier. An upwind building cannot be used to provide shielding on a slope with a gradient greater than 0.2, unless it is its overall height above a common datum such as sea level exceeds that of the subject building as shown in figure 4.2. If we look at this figure, upwell depending on a slope. So if this our wind direction, in this direction, and this our building, so this building is cause or can do shielding, but I think these are not. So this can cause shielding. So a shielding building as elevation exceeds building being shielded. So because this height more than the height of this is building we are studying, so this building can provide shielding because its height more than the building under study or under design. This one no shielding because average slope is more than zero point 0.2, elevation is less than building being shielded. This one shielding building as height is more than h and the average slope is less than zero point 0.2. So because this one on a slope more than zero point 0.2, so it doesn't do any shielding. This one because it is not on slope more than 1.2, so it can do shielding. Here also no shielding. Here is no shielding because no distance from the building is greater than 20h. So they have two factors affecting shielding. So we have or three. We have height, slope, and distance. So this one is the distance is more than 20 the height, so cannot do shielding. This one, the building height is less than the building height, the study building height, so it cannot do shielding. Okay, the shielding multiplier MS can be taken as 1 for a structure with h greater than 25 meter, where shielding can be ignored. So if the height more than 25 meters, so MS is 1. The shielding multiplier MS that is appropriate to a practical direction is taken as a table below. The shielding multiplier for building less than 25-meter height is depending on the shielding parameter S. So the shielding parameter S will give us the shielding multiplier MS. How to find the shielding parameter S? Before going to the shielding parameter S, we have building providing shielding. This is the define of building providing shielding. Only buildings with 45-degree sector of radius 20h, where h is building height. With height greater than or equal to h are used to provide shielding. This was explained here in this figure. Okay, what is the shielding parameter S? The shielding parameter S is determined as follows. S equal to LS over root HSBS, where LS is the average spacing of shielding buildings equal to H times 10 over NS plus 5, where NS is the number of upwind shielding buildings within a 45-degree sector. HS is the average roof height of the shielding buildings. BS is the average breadth or width of shielding buildings normal to the wind stream. And H is the average roof height above ground of the structure being shielded. Okay, so this is our formula for the shielding multiplier. S. Or sorry, shielding parameter S. Using shielding parameter S, you can find the shielding multiplier. The next multiplier we have is the topographic multiplier MT. So MT is the topographic multiplier The graphic multiplier MT is taken according to the following cases. Case for A, for sites in region A4. So for A4, MT equal to MH MLE times 1 plus 0.0015E, where MH is the Hill shape multiplier, MLE is the Lee effect multiplier taken as 1, E is the site elevation above mean sea level in meters. So this is the site elevation. This is 1. MH is the Hill multiplier, will be calculated later here. So this for sites in region 4. The next one is for region 0. For region 0, MT equal to 0.5 plus 0.5 MH, where MH also is the Hill multiplier. The third case is otherwise or elsewhere, the larger value of the following. So other cases, MT will be the larger of MH and MLE. So if MLE taken as 1, so the larger MH or 1. The next or the parameter needed in this case is the Hill shape multiplier MH. What is the Hill shape multiplier MH? The Hill shape multiplier MH is taken as 1 outside the local topographic zones in figures 4.3 to 0.4 to 4.5 in the Australian standard, and for each above 10, less than 10 meters. And these are the figures. Figure 4.3, 4.4, and 4.5. Okay, so this is the figures. So outside of the figures shall be taken as 1. Inside the figures, it will be calculated with the figures. Within the local topographic zone, the hill shape MH is assessed for each cardinal direction considered, considering the most adverse topographic cross-section that occurs within the direction range within 22.5 on either side of the considered cardinal direction. The values of MH are determined as follows. So MH for H over 2 LU less than 0.05, MH is equal to 1. If H over 2 LU above larger than 0.5 and less than 45.45, so this will be the value of MH. The third case, if we have H over 2 LU larger than 0.45, so within the rectangular peak zone, MH will be this value, which is M1 plus 0.71 times 1 minus x over L2. Elsewhere, within the local topographic zone, MH will be this value, which is 1 plus h over 3.5 times z plus L1, all times 1 minus x over L2, where h is the height of the hill, ridge, or escarpment, LU, horizontal distance upwind from the crest of the hill, x is the horizontal distance upwind or downwind of the structure to the crest of the hill, L1 length scale to determine the vertical variation of MH to be taken as the greater of L.36 LU or 0.4 H. So this one will be the larger of 0.36 LU and 0.4 H. L2 length scale as well to determine the horizontal variation of MH to be taken as for L1 upwind for all types and downwind for hills and ridge, or 10 L1 downward for escarpments. Z is the reference height of the structure above the average local ground level. Okay, for the case of where Z or X are zeros, the values of MH is taken as the following table. In some cases, X or Z might be equal to 0, so because the equation has like X and 0 uh, in the like here, so there will not be any value of MH, it will be 1. So the Hill multiplier factor MH will be taken from this table for if X or Z equal to 0. So for upwind, slope, and MH. So for these cases, you can find MH because for upwind, so this is the M hill parameter, and here is like the local topographic zones for hill and ridge escarpments, and hill and escarpments having upwind slopes greater than 0.45. So if the building is somewhere here, this is the height of the building, and so this will be the value of L ultimate, and this is L2, and this is H of the hill. And you can find the parameter for the cases using these figures. So if H is over 2L alt LU is less than 0.05, so take MH as 1. If H over 2LU between 0.05 and 45, so MH will be 1 plus H over 3.4 Z. So where Z here will be the building height. Plus L1 over X. X is the distance from here. So I will just remove this. So X is from here. So if you are here, so this is X, and this is the building height Z. So depending on the values, you can get the value of MH, and note that the hatched area is the local topographic zone, and if you are out of the topographic zone, you can take MH as 1. So here MH is 1 outside the local topographic zone. So this is for MH, and again, to remember, MH is required to find MT. So if you know MH, you can find MT. Okay. Now the fourth topic we have today is the